Francisco, come on up. We'll introduce ourselves. Thank you. Hello, my name is Burak Yenier. I think it's my 5th year at this event, so great to be back. But this year, unlike previous years, I'm just a sidekick. I'm just the opening act. Francisco will talk about a project that he worked on, and I will let Francisco introduce himself.
Good afternoon, my name is Francisco Sahli. I'm a PhD candidate here in mechanical engineering, and as Burak said, we have been developing a model of the heart to predict drug-induced arrhythmias, and I will explain it to you a little bit more in detail later after Burak's introduction.
Thank you. So I'll start by talking about a topic I know very little about, but I wanted to learn more. So there have been about 100 people who attended this conference in the last 2 days. And if we are a typical sample of US citizens, 25 of us will pass away and die out of heart disease. That's very heavy to think about. So it makes the presentation topic very relevant. How can we save lives by using high-performance computing? And if you look at the cost that cardiovascular disease has on the US economy alone, that's 1 out of every $6. I believe it translates to about $300 billion of economic hit per year. So figuring out a way to use a lot of computer power to solve heart disease sounds like a very, very good economic proposition as well as a technical challenge. So briefly about UberCloud and my background, we started looking at high-performance computing back in 2012 as a company. And the question that I was constantly wondering about was, how come we can't use cloud computing, which is very successful in enterprise already, for high-performance computing? And no argument that I heard was convincing enough. So that's what had UberCloud start with about 200 experiments. We literally went around asking people in the industry, hey, do you have challenging HPC problems that we can sink our teeth into? And every time we found one, we just jumped on it. We used cycles from any cloud operator we could find, AWS, Azure, Google. And we started running these experiments. And we started to get some very interesting results. We figured one of the things that's really broken, and I will touch on that in my presentation, was software distribution in high-performance computing. We work with very complex, tightly coupled codes. We care about parallelism. We care about pre- and post-processing. So when a lot of that came together, it was really interesting for us to look at a technology that we called containers, and we started writing a spec. Little did we know, another company, a small one in San Francisco called .cloud, was also working on something that we today know as Docker. And when we put all of that together, we had UberCloud. So we started taking high-performance computing applications, putting them into Docker containers, and creating a marketplace for them. And that got a lot of CAE, computer-aided engineering vendors, excited because they shared the same thought that software distribution in this industry is broken. And with the help of companies like Intel and Hewlett-Packard, here is where we are. So the Living Heart project is literally the tip of the iceberg. A lot of these technologies had to come together over the years to make it possible. So I briefly touched on the experiments that we started our company with. And there were a number of areas which started to pop up very, very often. One of them was security. Obviously, in high-performance computing, people work with data that's proprietary to them. They are generating insights that are their own trade secrets. They don't want these getting out. So we realized security was going to be big, and we looked for ways of handling that. I'll touch on how that was done in a great level of detail. Well, if you open up HPC, that spells high performance in there somewhere, so performance is quite important. So you need to run at near bare metal speed. That's the gold standard, and any kind of deviation from that is unacceptable. That's why for many years, virtualization technologies could not find a home in high-performance computing. And that's one of the reasons why software distribution was so difficult, because we couldn't use virtual images of any sort. We had to install applications on bare metal all the time. But again, that was a problem area. I touched on software, and usability happens to be challenging in high-performance computing, because under the usability umbrella, we talk about multiple access methodologies. So we want to access our applications with command line type of context. We want to be able to access them through a graphical user interface. We want to automate things. So there are a lot of different mechanisms that go into usability, and that makes it challenging in high-performance computing as well. And again, all of these problems pointed us towards the container technology, and that's what we started building as a company. So when I talk about high-performance computing, especially high-performance computing in the cloud, right-sizing the infrastructure is very important. Early on, when I was talking to the experiment participants, they continuously told me their HPC workloads run overnight. I was like, is there a secret handshake that I don't get? All of these workloads somehow finish overnight? What they weren't telling me was when they came in the morning, it was very annoying if the results were not ready. So they would cut all kinds of corners in their analysis to make sure that it would finish overnight. And thinking that these guys are designing stents for your heart or your car's brakes or your plane's wings, you really hope they're cutting the right corners. What started to appear as the right solution in my mind was, let them keep the complexity in the model, as long as it's valuable for the end result, of course. But let's right-size the compute environment. That sounds like a much better proposition. In terms of the next goal that I could see, faster time to resolution of the computations was very important. I sometimes hear, hey, Burak, I run my analysis and it takes a whole week. Well, you can't put your intuition on pause and say, well, I want my next intuitive idea in a week, please. Your mind just doesn't work that way. As long as you have intuition, you want your compute power to be there so you can keep running your computations. And enabling new capabilities, I won't talk about that at all, because you will hear that from Francisco, and how having computation power, brilliant engineers, and really good software can make a big difference. So I kept talking about containers. I'd like to open the technology a little bit more. When I say containers, I'm talking about Docker containers, to be very specific. We do work with other runtimes as well, but we believe that Docker is a great fit, especially if you're running high-performance computing in the cloud. Here's a view from one of our containers. It's fully graphical user interface enabled. You can, as an engineer, you can see your pre-processing, you can see your CAD geometry, and when the analysis is complete, you will be able to get your results back. And again, Francisco has some very interesting slides to show about that. In terms of what's running behind the scenes, it's a workstation-like user interface, so you see a desktop. However, in the back, it's GPU-enabled, so you can accelerate the graphics. It is MPI-aware, so you can run multi-node jobs, and it's also supporting InfiniBand and OmniPath interconnects in the back, so that you don't lose performance as you're running over multi-node. So the idea is, can we give an engineer an environment that they are finding as a pleasure to use, right, like a desktop, but make it behave like a high-performance computing environment. And that's what we have worked on. One of the benchmarks we have run was with Intel, and we had to prove that we were running at near bare metal speed. And when this study was done at Lawrence Livermore National Labs, we were very happy to see that inside containers, we can get bare metal-like performance, scale it up to hundreds of CPU cores, and GPU enable them if necessary. So again, engineers are getting best of both worlds in terms of both ease of use and performance. The platform that we used together with Francisco was we took an HPC as a service stack. Tried to say that out loud 3 times in a row. And the idea is, can you take a bare metal system, in this case, there's no hypervisor or virtualization going on. Can you take a bare metal system, run an HPC as a service stack on top, and enable users to have direct access to computer-aided engineering applications without having to install anything? So literally, the environment that Francisco worked on, it was created within hours, not days or months, in terms of setup time. The software did not exist on this hybrid cloud environment. It all came through containers, which is on the top layer, and the HPE orchestration stack for high-performance computing was used. So this stack is able to create an InfiniBand or OmniPath-like interconnect, slice and dice it so that you get a certain section of that interconnect. It provisions your storage, and it provisions compute environments for you. So it virtualizes on a bare metal basis. There's no hypervisor, and that's their key technology there. And on top, we're running Docker-based containers. I promised to talk a little bit about security, and then I'll turn it over to you. In terms of security, the inner core comes from the use of dedicated servers. So each container is running on a single server, and it occupies the entire server. So we're not talking about multiple applications running on the same server. That gives you very good sandboxing there. Your sandbox is your server. Then the network and storage segmentation is handled by the HPC as a service layer, which segments the environment into multiple chunks. And on top are the usual security protocols that you would see with your online bank or anything that's on the internet. So all of this coming together gives the user the ability to be in a secured, sandboxed environment, although they are in a third-party data center. So why don't I stop here, and I'll let Francisco take us through the Living Heart project.
So this is a collaboration that we did within the Living Heart project. I'm going to explain a little bit more what is that. With Stanford, my home institution, Simulia, we use the software Abacus. Advania was the hardware provider, UberCloud, and Intel and Hewlett-Packard. And first, what is the Living Heart project? The idea is to bring together researchers, industry partners, physicians, and regulatory agencies together to develop highly accurate and highly validated heart models that can be used for a wide range of applications. So, for example, if a medical device company would like to design a new device, this model can guide the design instead of testing this new device directly on an animal model, for example. And Another application and is what we have been doing for the last couple of years is to use this model or develop this model to see what are the side effects of drugs. So a little bit of background on drug development. Is a very, very expensive process. The average cost is about $2.5 billion, and only 12% of the drugs that are developed reach the market, and this process takes, on average, about 10 years. And the problem is that many drugs, not only cardiac drugs, can have side effects on the heart. And some of these side effects are sudden cardiac death, which in the US is around 300,000 deaths caused by this, but it's really unknown how many of these deaths are related to drugs. So we can take this drug that is called decimating, for example, and this drug was introduced in the year 1993, and it was in the market for about 7 years. And there are 80 fatalities that are directly associated with this drug. And this drug has nothing to do with the heart, but it still can cause side effects. On the year 2005, a new regulation was introduced to prevent the introduction to the market of this kind of drugs, but you can see that the number of arrhythmias that are related to drugs has not decreased. So what we did is we developed a high-resolution multiscale model of the heart that you can see here. It's a finite element model. We get a resolution of nearly simulating every cell in the heart. So we have 7 million finite elements. And because we want to accurately represent the cellular dynamics, we have 250 million internal variables that represent different concentrations and different dynamics of ionic channels. And if we want to simulate only 5 bits, this takes 1 million time steps. We also differentiate in 4 different cell types that you can see in the different colors in this picture. So Burak already explained a little bit how we did this. We did it with an UberCloud container, and it was really nice, especially for the development stage, because I had to try a lot of things that will be hard in like a bigger cluster to see what's the output of the model very quickly. So we use Abacus as the software to run this model. And the model scaled pretty well up to 240 cores, and so we ended up using 160 cores, and one simulation that I'm going to show you took about 40 hours. So here are some results. So here you can see the baseline model where we don't apply any drug. On the bottom you can see the electrocardiogram. You can see that the heart activates. That means it turns orange, and then it turns blue back to a resting state again. And this happens very periodically, as it should be happening to our hearts now. Now if we apply a low-risk drug, a drug that we know that doesn't affect the heart that much, you can see pretty much the same pattern. I mean, I can tell you that the time it takes to go back to resting state is a little bit longer, but there is really not much of a difference. So now if we apply a high-risk drug that we know that it causes arrhythmia, we can see the spontaneous development of this disorganized rhythm in the heart. So you can see that the rhythm is not periodic, and what will happen in this case is that the heart is not contracting in a coordinated way, so it will not be able to pump blood efficiently.
Thank you, Francisco. So one thing I'd like to point out there is those were post-processing results that came from the computer simulation. And the results of that can be easily read by a physician because they can literally see the heartbeat. And it's so amazing to me that you can do that without having to literally induce the drug to a human being. The heart model is completely parametric, so that could be your heart. It doesn't. This one is a generic heart model. However, it can be customized to fit your heart model, and they can try different compounds and the effects of that on the heart without having to induce it on a human being or any kind of animal testing.
Is the geometry parametric?
The geometry is parametric, yeah.
And the meshing as well?
The meshing is applied after the parameters are changed. So yes, so that's very valuable because now you're talking about personalized medicine and a drug that may have a negative impact on a person may not necessarily have the same effect on somebody else. So it's very inspiring to be able to see brilliant engineers do that kind of work and solve problems before they affect us in our real lives. Any other questions? Yeah?
So I'm assuming this was abacus explicit, not abacus standard.
Yeah, it was explicit. Actually, we started with abacus standard, but it was like way slower than explicit, and then we switched to explicit. Yeah.
And how do you compare your cloud to the Rescale cloud, for example? Are you familiar with that?
Yeah,
What is the differentiation?
absolutely familiar. So one of the things is this is a bare metal environment. It's not necessarily a public cloud with some kind of virtualization running on it. And number two, we took the interactivity to the most level you can take it. So literally, Francisco was working on the environment through a desktop user interface. And his comment about that was, especially at the early stages of a project, where you don't necessarily have your model and your variables completely locked in, you're in a very experimentational mode. You really want to change things, literally almost like an Excel sheet. Change things, see their immediate result, and keep trying. And the batch model of HPC that we are so used to through a command line interface is not a good fit for that. So a lot of the other providers have chosen paths which are much more in tune with batch, but we wanted to go very interactive in our approach. That's why the Docker containers are a great fit. Yes?
What did you do to the Docker containers to allow you to have a graphical user interface running in the container?
Right. I'll tackle that one as well. Docker containers allow you to run services inside of them. So there's really nothing that prevents you from running the desktop graphical user interface as a service inside of the container, and then allow that to be remotely viewed. So here the mechanism that we used was literally pixel shipping using VNC to allow an engineer working here in Stanford campus to see the HPC as a service environment, which was actually running in Europe. The Advania data center is in Iceland. So imagine the possibilities. Yes?
Is your HPC AAS running in a cloud environment?
The Advania data center we talked about is a cloud environment. However, it is bare metal. It is not a hypervised environment. That's what gives us the additional performance boost.
Is a bare metal cloud?
It is a bare metal cloud. Yes, in the back.
A couple quick things. You said 7 million elements, 250 million unknowns, right? And can you talk a little bit about both the hardware environment as well as the model and the solver that was used to get a better idea of because the scalability to 240 compute cores, that's not a lot. So why? Well, because 60 hours is an enormous amount of time, especially if you're doing parametrics and if you want to do what ifs, right? So if you want to bring that down, What kept you from scaling up to a much larger usage in the cloud?
Yeah, again, this is a good question. So when you talk about scalability, there are multiple factors in effect. One of them is obviously the code that you are using. Codes will have their sweet spots in terms of scalability, and that's really a factor of the math that they are using inside of their code. How much can you scale it? Number two is the hardware infrastructure you are running on. So we talked about the effect of interconnects, whatnot, so that affects you. And number three is your model. So depending on what your model's scalability pattern is, you will be seeing diminishing returns at some point. So a lot of the benchmark models that we see showing linear scalability, up and to the right, those are designed to have a large scalability effect so you can test your hardware. That doesn't necessarily mean your models will always scale to that effect. So what we advise to our customers when they first show up at UberCloud is we say, let's try to go 2x. Whatever you've run it, whatever was your maximum, let's just double it first. And we start going up until we find where the bottlenecks are. And the bottlenecks could be in network optimization, they could be in give me an accelerator, or let's change the model so the mesh is better suited to be scaled up. So all these factors play an important role. Now, in terms of why we didn't go any further, because this was not an academic exercise in terms of how far can we scale it, we were more interested in the results that Francisco could read. So we achieved what we wanted to with 240 cores.
So like how many nodes was in there? What was the characteristics of the nodes? Were there accelerators or GPUs?
Yeah, I have all of that. I'll be happy to share it right after this. This is definitely not supercomputing scale. Yes?
In one of your first slides, you talked about that usability or user experience is pretty important. And
right.
You showed the screenshot with this remote desktop through
right.
the browser. That's where, in my experience, it's like, especially when there's a lot of mouse interaction, it gets a bit buggy, or even a short delay will limit my user experience. Did you do some usability tests, or have you some experience? Because I would be skeptical just from
Francisco, why don't I let you handle that? When you were using the desktop interface, what was the lag time? How did it feel?
I think in terms of lag time, it was pretty good. In terms of resolution, I mean, the cluster was in Iceland, so it was not, it was pretty far away. But in terms of resolution, it was not what I will have in my desktop, but it was still usable for sure.
So let me add also some commentary on top of that. We do not see the desktop interface of the high-performance computing machine as a replacement to the desktop. The user always has the ability to pull the data back and do more slicing and dicing. So never see that as a replacement. However, when there is high latency and very fine meshes where we would like to visualize further, we didn't do it in this specific case, but we have the ability to deploy with GPUs for rendering. So in those cases, your question is very valid. When you rotate a 3D geometry, for example, when you're sending pixels across, well, how does that work, right? It starts from the top of the screen and literally traverses every line. The trick that you can apply to that kind of a, let's say, remote distance problem is you take the entire output and you compress it into a video stream. Then you cannot see the tearing or the bits being displayed anymore, and you get a much better user experience out of that. We didn't use that technology here, but it is an option. Great question. Any other questions, comments? Yes?
To be honest, I did not get, it was impressive with this drug testing to the hearts, but I did not get what was the real input from the drug. So how did you sort of say, yeah, why did you know that this drug is affecting it? So I didn't get what were the input.
Yeah.
Yeah,
I didn't explain that. So in experiments, you can measure how much each drug blocks each ion channel of the cardiac cell. So those experiments are the inputs of my model, because I can model every ion channel on a cardiac cell in the computer. So I directly apply these experimental measurements to my model.
Sorry, but still, your drug is like, I don't know, a chemical representation, or what did you use for this, that you know that this actual pill?
Yeah. So so no, I use experiments. So I mean, it's literally they take a cardiac cell and put the drug on it and measure how it affects the drug. The nice thing is that I can take that individual cell experiment and project it to the entire heart and have an electrocardiogram and have arrhythmias or not, and that you cannot see in a single cell.